of beta eta. Should be squared, squared, squared. This is equal to beta, the norm m2 eta squared. Well, we know that this is less than or equal to beta squared norm eta squared. But eta squared is norm 1. So this is beta squared. And this is less than or equal to 1. So that tells us that all of these are equalities. And we get the norm beta squared equals 1. Well, from this, 1 equals alpha squared plus beta squared. Well, 1 is the absolute value of alpha squared plus absolute value of beta squared. Therefore, alpha is 0. And we're done. We have the C1 and the C2 have to be orthogonal. Now you can reorder your PCIs and your MIs. So any PCI is orthogonal to Cj for I not equal j. What time? We're almost done. I would like to get through distinguishability. So you have this theorem. What's a corollary? Suppose you have a state space Hs. Then Hs has at most the dimension of Hs perfectly distinguishable states. That's perfectly distinguishable. It's a very strong condition. One more theorem. Let C1, Cn be states in Hs. But then be linearly independent. There exists a set mi, 0 less than or equal to I less than or equal to n. So there exists a measurement system, mi, where mi Cj does not equal 0 if and only if I equals j. So we lose orthogonality, meaning we lose this as 1. We lose probability 1. how are we going to get this? Let VI be the span of Cj where I does not equal j. So we're going to let VI be the span of the vectors that aren't Cj. Note, and here's the important note for this theorem. The Ci is not an element of Vi. We get that because they're linearly independent. Okay? Let EI be the projection onto Vi perp. Okay. So EI is a projection. So 0 is less than or equal to EI is less than or equal to the identity matrix. Now we get 0 is less than or equal to the sum I equals 1 to n of EI is less than or equal to n times identity matrix. Finally, we get zero is less than or equal to 1 over n. Sum I equals 1 to n. EI is less than or equal to the identity matrix. Okay. Let mi equal 1 over the nth root of EI. Also, let m0 equal I minus the sum 1 over the square root of n EI one over sum over n EI to the 1/2. Since I is greater than or equal to the sum 1 over n EI, we know this is positive. So this makes sense. Namely, m0 star equals m0. So what happens when we sum up the mi's? The sum, I equals 0 to n, mi star mi, right? This we want to be I. This equals m0 star m0, which is this guy. I minus sum 1 over n ei. I minus sum 1 over n ei. I equals 1 to n. Plus sum, well, mi is 1 over the square root n ei, where ei is a projection. So that's 1 over n ei star, which is 1 over square root of n ei, times 1 over square root of n ei, which is just ei 1 over n. I equals 1 to n. This and this cancel. So this is I. So at the very least, these m's is a quantum measurement system. Okay? Now remember what I said was the important fact. The fact that the Ci is not in Vi, and Ei is the projection of these Vi's. So, if I does not equal j, the Cj is an element of EI, right? But I took the orthogonal projection of VI to get EI. So, EI, Cj, is 0. So, Mi of Cj, which is 1 over the square root of n EI, for Cj, must be 0. Now, let I equal j. Well then, the Cj is not in Vi. Well, we'll stick with I. Ci is not in Vi. So, Ei of the Ci does not equal 0. Then, the norm of Mi Ci, which equals 1 over the square root of n, norm Ei to Ci, say squared, this isn't 0. So the norm can't be 0. So this is not 0. And we're done! Okay, so today we've discussed a background of vector spaces. We've discussed what a direct sum and a tensor product mean. We've described Hilbert spaces and given examples. And we've discussed quantum measurements and the distinguishability of pure states. Thank you.